Radioactivity is a fascinating phenomenon where unstable atomic nuclei transform themselves into more stable configurations. This transformation involves emitting particles or energy, and beta decay is one such process. In essence, beta decay is a type of radioactive decay in which a nucleus emits a beta particle, transforming into a different nucleus with a different number of protons. Imagine a popcorn kernel suddenly popping. That's a simple analogy for how an unstable nucleus undergoes beta decay. Beta decay plays a crucial role in the study of nuclear physics and has significant implications for various fields. It helps us understand the fundamental structure of matter, the processes occurring within stars, and even has applications in medicine and archaeology. Understanding beta decay is like unlocking a door to the hidden workings of the universe at the tiniest level. It's a fundamental process that governs the behavior of atoms and has shaped the world we live in. This essay delves into the intricacies of beta decay, providing a clear and concise guide to understanding this important nuclear process. Beta decay can occur in two forms, beta minus decay and beta plus decay. Both involve the transformation of a neutron or proton within the nucleus. Think of it like this. In a game of tag, one person tags another, instantly changing roles. In beta minus decay, a neutron transforms into a proton, emitting an electron, called a beta minus particle, and an antineutrino. This process is like a negative charge escaping the nucleus, leaving behind a more positive environment. On the other hand, beta plus decay involves a proton transforming into a neutron, emitting a positron, the antiparticle of the electron, and a neutrino. This is analogous to a positive charge escaping, leaving the nucleus slightly less positive. Understanding these two types of beta decay is crucial for comprehending the changes occurring within the nucleus during these transformations. The Q value in beta decay represents the energy released during the decay process. It's like measuring the pop of the popcorn kernel. The more energy released, the louder the pop. The Q value is crucial for determining whether a particular decay is energetically possible and for understanding the energy distribution among the emitted particles. Calculating the Q value involves comparing the masses of the parent nucleus and the daughter nucleus, taking into account the masses of the emitted particles. The difference in mass, converted to energy using Einstein's famous equation E equals mx squared, gives us the Q value. A positive Q value indicates that the decay is energetically allowed, meaning it can occur spontaneously. Conversely, a negative Q value implies that the decay is forbidden, as it would require an input of energy. Understanding the Q value is fundamental for predicting and analyzing beta decay processes. Let's illustrate the process of solving beta minus decay problems with an example. Consider the beta minus decay of carbon-14, a radioactive isotope used in carbon dating. Step 1. Write the decay equation. Carbon-14 decays into nitrogen-14, emitting a beta minus particle and an antineutrino. Step 2. Determine the atomic and mass numbers. Carbon-14 has 6 protons and 8 neutrons. Nitrogen-14 has 7 protons and 7 neutrons. The beta minus particle is an electron, so it has an atomic number of -1 and a mass number of 0. Step 3. Calculate the Q value. The Q value is calculated by finding the mass difference between the parent nucleus, carbon-14, and the daughter nucleus, nitrogen-14, considering the mass of the emitted electron. Using the atomic masses from a table, we can calculate the Q value. Step 4. Analyze the results. A positive Q value confirms that the decay is allowed. The calculated Q value provides insights into the energy released during the decay. By following these steps, we can systematically solve beta minus decay problems and gain a deeper understanding of the decay process. Section 5. Tackling beta plus decay problems. Solving beta plus decay problems follows a similar approach to beta minus decay, with some key differences. Let's consider the beta plus decay of potassium-40, a naturally occurring radioactive isotope. Step 1. Write the decay equation. Potassium-40 decays into argon-40, emitting a positron and a neutrino. Step 2. Determine the atomic and mass numbers. Potassium-40 has 19 protons and 21 neutrons. Argon-40 has 18 protons and 22 neutrons. The positron has an atomic number of +1 and a mass number of 0. Step 3. Calculate the Q value. Q equals the mass of potassium, 40 minus the mass of argon, 40 minus twice the mass of an electron, all multiplied by the speed of light squared. Note that we subtract twice the electron mass because a positron is emitted, and an electron is effectively lost from the atomic electron cloud. Step 4. Analyze the results. As with beta minus decay, a positive Q value indicates an allowed decay. By accounting for the differences in particle emissions, we can apply the same fundamental principles to solve beta plus decay problems. Section 6. Electron capture. A closer look. Electron capture is another type of radioactive decay that resembles beta plus decay in its outcome. In this process, an atom's nucleus captures one of its inner orbital electrons, combining it with a proton to form a neutron and a neutrino. Step 1. Write the decay equation. For example, the electron capture of potassium-40 can be represented as potassium-40 plus an electron yields argon-40 plus a neutrino. Step 2. Determine the atomic and mass numbers. The atomic and mass numbers are balanced in this equation, with potassium-40 having 19 protons and 21 neutrons, transforming into argon-40, which has 18 protons and 22 neutrons by capturing an electron. Step 3. Calculate the Q value. The Q value calculation for electron capture is similar to that of beta plus decay, considering the mass difference between the parent and daughter nuclei and the mass of the captured electron. Step 4. Analyze the results. A positive Q value indicates that electron capture is energetically allowed. Electron capture is an important process in nuclear physics, contributing to the transformation of certain radioactive isotopes. Section 7. Classifying decays as allowed or forbidden. Not all beta decays are created equal. Some decays occur readily and are considered allowed, while others are highly unlikely and termed forbidden. This classification depends on the changes in angular momentum and parity during the decay process. Selection rules. Allowed decays involve small or no changes in angular momentum, which is delta L equals 0 or plus or minus 1, and no change in parity. They occur with a high probability. Forbidden decays involve larger changes in angular momentum, which is delta L greater than or equal to 2, or changes in parity. They are less probable and occur at much slower rates. The degree of forbiddenness, such as first forbidden, second forbidden, and so on, reflects the extent of angular momentum and parity changes. Understanding these selection rules helps us predict the likelihood and characteristics of different beta decay processes. Section 8. Common mistakes and how to avoid them. When solving beta decay problems, it's easy to make mistakes, especially when dealing with atomic and mass numbers. Here are some common pitfalls and tips to avoid them. Incorrectly assigning atomic numbers. Remember that beta minus decay increases the atomic number by 1, beta plus decay decreases it by 1, and electron capture also decreases it by 1. Miscalculating mass numbers. Ensure that the total mass number on both sides of the decay equation is balanced. Forgetting the neutrino or antineutrino, always include the neutrino or antineutrino in the decay equation, as they carry away momentum and energy. Ignoring the electron mass in Q value calculations, for beta plus decay and electron capture, remember to account for the electron mass, as it affects the energy balance. By being mindful of these common errors and following the step-by-step guides, you can improve your accuracy in solving beta decay problems. Section 9. The significance of beta decay. Beta decay, while a seemingly esoteric nuclear process, has profound implications for various fields, impacting our understanding of the universe and our everyday lives. Nuclear medicine. Beta decay is the foundation for various medical imaging techniques, such as PET scans, and for treating certain cancers through targeted radiation therapy. Archaeology and geology carbon dating, based on the beta decay of carbon-14, revolutionized our ability to determine the age of ancient artifacts and geological formations. Astrophysics. Beta decay plays a crucial role in the processes that power stars and the creation of elements heavier than iron in supernova explosions. Nuclear energy understanding beta decay is essential for the safe operation of nuclear reactors and the management of nuclear waste. By studying beta decay, we gain invaluable insights into the fundamental forces governing the universe, leading to technological advancements and a deeper appreciation for the intricate workings of the natural world.